Hello, welcome back to part 2 of PTC's annual Submarine Cable Workshop. Thanks again to Sean and all of the Around the World panelists for a wonderfully informative first session of our workshop. For this part of our program, we've lined up another set of experts who will shed light on a spectrum of opportunities and challenges associated with today's undersea sensing capabilities, which are now being built into new transoceanic commercial networks. The possibility of such networks serving both commercial and research interests has been in discussion for many years. To see them finally become reality is terrific. Today's set of panelists have been recruited by my friend, Tony Mosley from OSI, who will moderate the panel. I'm fully expecting to be fascinated, and I imagine you will be too. Before I turn it over to Tony to introduce our panelists, let me once again thank our sponsor, Suboptic, and also encourage you to tune in tomorrow for the final portion of our workshop, where we once again will benefit from a truly esteemed set of panelists who will reflect upon the impact of geopolitics on our industry today. I'm hopeful it will be the piece de resistance of PTC'21 Submarine Cable Workshop. Tony?
Aloha, half a day, and welcome to PTC'21 Submarine Cable Workshop. Thank you so much, Elaine, for the terrific introduction. As is one of the three musketeers, I salute you. Paul McCann, that goes for you too. Thank you so much for your support and guidance on this journey. I'd also like to thank Sharon and the PTC staff, especially Jen, for all the hard work in getting these sessions organized. We do appreciate your work. Lastly, and most importantly, I would like to thank our sponsors, Suboptic, and all of the sponsors, for without sponsors, much of this would not be possible. Thanks to all of you. Today's session on submarine cables, distributed acoustic sensing, and marine data sovereignty, that's a bit of a mouthful. We have a distinguished panel of experts that will address some of the background, some of the historical firsts in the industry, a pure commercial telecom cable with ocean observing capabilities. Today's 420 plus submarine fiber optic cables represent millions of kilometers of infrastructure on the ocean floor. The subsea infrastructure potentially represents the opening of a new window into Earth's movement and subsea oceanographic research. For the past 10 years, the Joint Task Force led by Dr. Bruce Howe at the University of Hawaii has been working hard with governments, commercial businesses, cable suppliers to introduce new ocean observing capabilities into submarine telecommunications cables, known as smart cables. Dr. Bruce and the team have had some successes, and the work of the past 10 years for the Joint Task Force is beginning to bear some fruit. Some of the JTF work and some of the bold steps taken by cable suppliers and developments and government partners has led to one of the latest commercial telecom subsea projects, EllaLink, building ocean observing capabilities. And we're honored to have Gavin Moran in today, sitting in for Philippe Dumont, who is currently at one of the landings today. Gavin will share the latest on the project shortly and speak to some of the GeoLab genesis. EllaLink is one of the first commercial telecom cables to support ocean observing facilities, but it came as a result of GEANT, a government science organization supporting the project as a partner in GeoLab. Chris Atherton will be joining us, and he is a researcher in GEANT, and he will provide some insights as to the thinking from an investor standpoint in EllaLink. The research science and science information undertaken in EllaLink revolves around DAS, or distributed acoustic sensing. DAS and EllaLink, plus some new innovations and developments such as State of Polarization, are pushing ocean observing techniques forward. EllaLink and its cooperative partner, GEANT, ANACOM, and others will be one of the first of its kind to develop ocean observing capabilities along with telecommunications infrastructures. These kinds of public-private investments in submarine cables will set a new operating standard for future cable projects. But as these innovative capabilities in submarine cables concern regulators and nation states, these issues must be addressed and mitigated to unlock the capabilities to support the greater good. The legal community and UNCLOS, the auspices, must allow for these new predictive marine data sets from submarine cables to support long-term research, science, cable maintenance, and analytics, to support earthquakes, tsunami early warning. This new rich set of data will have marine sovereignty issues, which will be of concern, no doubt. But Kent Bressie on this panel will address some of that legal work ahead. For governments and regulators to get comfortable with research science. Again, this is a new innovative technique and a new partnership, and we look forward to more public-private partnerships. Again, thank you for joining us to kick off this second cable session, and thank you to all our sponsors. And I'll turn it over to Gavin to kick things off. Gavin.
Super. Thanks, Tony. Let me just share my screen quickly for everybody.
Great. Thank you.
Now, can everyone see? I suppose only the guys in the panel can say, but can the guys in the panel see?
All good.
Yes.
All good. Fantastic. So thanks again, Tony, for the introduction. As has been said, my name is Gavin Moran. I'm the Sales Operations Director at EllaLink. And for those of you disappointed not to see our CEO, Philippe, today, for good reasons, he's not here. He's had to take some travel at the last minute to Madeira because we've got a good weather window and we should be landing our cable in Funchal this week. So for me, I got the call up at about 7 Eastern, more or less 11:30 midnight last night to do this. So as a Saints fan, for those of you who follow football, this was a nice distraction to prepare notes for this away from what was going on in the field. So what I'll do is I'll do my best to fill in his shoes. So be nice. Firstly, as you can see on the screen, I'm going to give a little quick introduction to EllaLink. So what is EllaLink? Who are EllaLink? It's a new high-capacity submarine cable system between Latin America and Europe. It's the fastest and most direct connection between Brazil and Portugal, and will have branching units to Cabo Verde and Madeira. In the last few weeks, we've had successful landings in both Fortaleza in Brazil and in Sines in Portugal. And for those interested, there's some really good videos of those landings on our social media sites. This week, as I've said, we should be landing in Madeira, and Philippe and some other members of the team are traveling there this week. From a delivery perspective, after some slight COVID-induced delays, I'm pleased to say that we're on track for an RFS in May 2021. But enough about that. Today, we're specifically talking about the Madeira branch, and I want to focus on what we call the EllaLink GeoLab. So when did it start? The EllaLink GeoLab project began at the start of 2020 with the aim of being the first permanent infrastructure dedicated to DAS embedded in a commercial subsea telecom system. We decided to include an extra fiber pair on our branch to Funchal so that it could be dedicated permanently to this technology. We see our objective as the infrastructure provider to put our infrastructure at the disposition of others, because there's no magic to putting a fiber in a cable. It's not a new technology. And we've worked really hard over the last 12 months with our partners, namely EMACOM, ANACOM, GEANT, and FCT, to put together this project to a point of where we're now confident that we will be RFS in May 2021. What's really innovative about this GeoLab is the ecosystem that we've put together with GEANT, ANACOM, EMACOM, and FCT. EMACOM and EllaLink will provide the infrastructure, ANACOM and FCT, the government sponsorship and the access to the data, and GEANT, as the research network, will collate the data. For this point, I've been asked to highlight a couple of our partners specifically, Jose Barros and ANACOM, who have always been supportive of the EllaLink project and the inclusion of the GeoLab initiative within this. Without him, we would not be here today. And secondly, GEANT, who've invested in the EllaLink project from end to end. And without GEANT, this project would not have happened. So thank you to both. Each member of the team is a specialist and it's a component building brick, and we each have a defined role with knowledge and expertise. One other point of clarification to make here is that GeoLab was never formally requested. It was never a requirement for any license acquisition. EllaLink firmly believes that this equipment being installed will help and benefit the scientific community at large and bring a much greater clarity by providing real-time data on subjects such as seismology, volcanology, marine ecology, and a variety of others which are key to understanding climate change in the Earth's environment. So it's really important that we are the first in the submarine cable to integrate smart cable concepts. So you ask, why would a private commercial cable owner get involved in this? There may be risks, there may be other things which have to be considered. So other than the benefits of giving back to the scientific community, there are things which our cable can gain from an initiative like this. And the answer lies in the technology itself, the distributed acoustic sensing. The DAS can be a great tool for further protecting cables. The first element of protection that we see is in terms of suspension. The DAS has the ability to identify suspension in the cable as soon as it's laid, giving the cable vendor a chance to rectify this in the post-lay inspection and burial activities. So this is a crucial benefit. The second is in detecting surface vessels, which could create a possible danger to the cable in terms of fishing and anchorage. DAS has a capability to provide real-time data on both of these, so there are considerable tangible protection benefits for our cable. For these and other reasons, we believe it's a really good idea. The technology itself is non-invasive, it's economical. We don't need to add any active equipment to the system, which adds complexity and cost. The DAS doesn't penalize the performance of the telecom system because after all, we have to consider that EllaLink first and foremost is a telecom system. The benefits of giving back to the scientific community, they're clear. You know, our objective with our partners was to create an ecosystem of multiple organizations working together with a common goal to give real-time data on ocean conditions to the scientific community. And we believe we're doing this. The Portuguese government and the regulator ANACOM have been a key driver of this project from day one. It's a smart cable concept, but as we call it in EllaLink, it's the GeoLab. The GeoLab itself will include sensors within the cable. The DAS will send a signal down the cable at a particular frequency, which is capable of listening to microstrains. So kind of like a microphone, a little bit like an OTDR, but much more sensitive. The magic, though, is in the ability to analyze the flow of this data. How it's going to work from an EllaLink perspective is, look, there's no point in pretending we're not the experts in this technology. It's a piece that guys will go into in more detail later in this presentation. We're going to deploy an additional fiber from our CLS in Madeira to the branching unit on the main system. The DAS equipment will be installed, as you can see here, in the EMACOM on point 1, in the EMACOM CLS, all the way from the CLS out to the branching unit itself on the main system. The data recorded by the equipment in point 2 will be made available in FCT's network, and the data will be distributed on the GEANT network, which will apply data sharing and control policies. Again, to reiterate a point, we're actually installing the branch this week, and hopefully we'll be able to do some testing with Febus immediately after the deployment. Overall, what I can say from an EllaLink perspective is it's been a really great experience so far. It's really working as a project. And again, as I've said, to see multiple organizations working as one for the benefit of the global scientific community has been fantastic. What I can say also is that it's our intention for future landings to include additional fiber pairs, specifically Tenerife and Mauritania, to benefit the wider community if it makes scientific sense. Our hope is to be the leaders here and to make it a success, because there's nothing stronger than a good example for others to follow. And I think at this point, it's a good time to hand over to my friend Chris and GEANT, who can go into more detail. Thanks for listening, everyone.
Thanks very much, Gavin. And yeah, thank you very much, Tony, as well for the introduction. So my name's Chris Atherton, and good morning to everyone who's joining today. I'm a Research Engagement Officer at GEANT. And GEANT is a pan-European research and education network. So we procure fiber connectivity from commercial providers in order to connect up national research and education networks across Europe. And there are 43 national research and education networks who work with us. Most of them are our owners as well. And then we then connect up Europe out to the rest of the world. FCT, the Portuguese ENREN, are one of our members as well, and that's important to realise, because without the support of FCT, the GeoLab project wouldn't be able to come to fruition. So in terms of what GEANT can do to share the data out, we run a terabit network at the moment, and we're in the process of upgrading our backbone network to support exascale communication. Following that, we've also invested as part of the Bella consortium into the EllaLink cable between Portugal and Brazil. So just to explain a little bit about the reason for that, Bella building the Europe link with Latin America. This provides for the long-term interconnectivity needs of the European and the Latin American research and education community by procuring and deploying a long-term IRU or indivisible rights of use for spectrum on the EllaLink cable. And this particular project as well also helps to deploy 100 gigabit capable research and education network capacity across Latin America, and that's known as Bella T or Bella Terrestrial. Funding for Bella is provided by the European Union and the Latin American NREN community. And we're hoping that Bella will change the worldwide connectivity map and revolutionize the collaboration between the science and academia in Europe and Latin America for the next quarter of a century. There's more information on Bella if you want to have a look at bella-program.eu, and we can provide some information for that in the chat at the end of the presentation. So GEANT is interested in GeoLab because it represents a world first of being able to provide a societal benefit to researchers globally for performing lots of different types of research, such as seismology, continental plate shift, or plate movement rather, ocean seabed interaction, benthic flows, research into benthic flows, abiotic and biotic marine interactions, and also cytology, or the study of whales and other mammals such as dolphins and things in the ocean. But what's important to realize is that the sensor itself is only localized to that 75-kilometer region between Funchal in Madeira and the main branching unit, as Gavin said before. Through this investment from the European Commission, which is about 26.5 million, we hope that the support for, or the initialization of this main EllaLink cable will greatly improve scientific collaboration between Europe and Latin America, but also our involvement has helped to realize or to see the GeoLab come to fruition. What GEANT will be able to do is provide access to the research and education community and act as the point of contact where we can get in touch with different scientific bodies to let them know about this new facility. And we really see the social benefits as being the main driver for this. So things like potentially investigating a tsunami warning system, and in 2017, Portugal set up a new tsunami warning center, and something like GeoLab would be able to support the work that they do, as well as earthquake detection. And as Gavin mentioned before, there's the ability for a facility like this to analyze suspensions and to be able to try out and test out new forms of testing and collaboration of the equipment that is used when installing submarine cables. And also, of course, is the long-term research that goes into continental plate movements and also Earth observation activities, or in situ Earth observation activities. So we've spoken a lot, or Gavin spoke a lot about DAS, the distributed acoustic sensor, and I'll leave it to Vincent to talk more about DAS and the technology behind it. But just to also mention that the GeoLab itself will be able to support not just DAS, but other types of technology, such as distributed strain sensing, polarization of light, and an optical time domain reflectometry. And it's hoped that the GeoLab will be able to accept participation from other research groups around the world in order to access the lab to perform tests on this cable. While there are no research groups using the cable, then we are looking to try and implement a DAS and find some funding to implement the distributed acoustic sensor, so we can use the cable to its full capacity or to its full potential. In terms of the data access, obviously the data is going to be generated in Funchal in Madeira, but then we're working with FCT, the Research and Education Network in Portugal, to see if we're able to then move that data from Funchal back to Portugal using the EllaLink cable. Once it's in Portugal, we're hoping to be able to acquire some data storage within Portugal, which researchers will then be able to present the data onto in order for it to be sent out around the world. And we're looking for those research groups that come to use the GeoLab. They'd be able to keep their data secure. Obviously, it will be made available to national and local authorities, but they'll be able to keep their data secure for a period of time before it's then shared more widely with the global community. When a research group is not using the GeoLab, then the data will be released after a short period of time, so that again, the global research and education community can utilize the data to the fullest extent. The way in which we'd like to try and distribute the data is that we will make it available on an FTP repository and notify the various research communities of the data being available, and they'll then be able to download it themselves in order to process it and then provide it to their own communities. So we GEANT ourselves don't want to be the single point of failure in this. We want to be able to utilize the existing research groups, research communities that are already out there doing world-leading research, and to support them in those activities. At the moment, we're working on a white paper to put together not only the data dissemination policies, but also the governance structure which would go into supporting the GeoLab itself. And we're hoping to have that released in the next month or so, so within Q1. And that's all from me. So thank you very much for listening, and back to Tony.
Thank you, Chris. I appreciate it, and thanks for the background. It's important work and extremely critical for the industry. That DAS infrastructure, one of the leading companies that are working in that field, Phoebus Optics, led by Dr. Vincent Lantique, he will discuss DAS and its infrastructure in EllaLink, and kind of bring us up to speed on the next level of infrastructure requirements for DAS. So, Vincent?
Yes. So, hello, ladies and gentlemen. I think you can see my screen right now. So, I will present you. I will tell a little bit about distributed acoustic sensing, and I will take an application on submarine cables, which is of interest to us today. So I'm Dr. Vincent Lantique, and I'm the technical manager of Phoebus Optics. So I will present my company just in one slide. So we are a manufacturer of distributed optical fiber sensing systems. We are based in France, in Pau. We are spending a lot of time and effort in R&D to increase our solution portfolio for being at state of the art of monitoring solution. So we mainly focused on oil and gas, geothermics, cable monitoring, and umbilical monitoring, which is basically the same requirements in terms of technology, perimeter security, and seismic acquisition. So here you have some antennas of Fiber Optics. So headquarters are in France, but we have antennas in Houston, and soon in Saudi, and recently in Strasbourg and in Tunisia. So we have a huge test facility in France in order to simulate and to demonstrate our solutions. So here you have some deployments from Fiber Optics all over the world with some of our customers here on the right. So how distributed sensing works. So you have a surface equipment, which can be in the land or on a boat, and you connect this equipment to an optical fiber, which is part of an optical fiber cable, which can be onshore or offshore. And then you will launch this pulse of light into this fiber, and it will propagate into the fiber. And during its propagation, a small part of the light is propagating backward. This light is generated at the point where the big pulse is, and its properties are dependent on some parameters one can measure. One of these parameters is acoustic wave. So the measurement is called distributed acoustic sensing, or DAS, which is the topic of today. But you can also measure temperature or strain with the same process, but with different equipments. So Fiber Optics has patents and has technologies to address temperature, strain, and acoustic sensing, which is the topic of today. So here are some specifications. I won't bother you with all those, but just a couple of things I want to highlight. Here you have the noise floor of the device, which is calibrated from 10 minus 3 hertz to 10 plus 3 hertz, 1 millihertz, 1 kilohertz. So you can have access to microseismic data, seismic data, and acoustic data, which is very important. But the more you go high frequency and long distance, because we can go up to 50 kilometers, the more data you will collect. And this is one challenge on collecting DAS data, is the amount of data. Can be terabytes a day with one DAS and only 50 kilometers. So that's one thing. The other thing is the range is 50 kilometers. So we cannot address all a link from Europe to US, for example. No, we can address only the closest part from the equipment, the 51st kilometer. We will see there are some ways to expand a bit this figure, but it's 100 and 150 kilometer at maximum. So, of course, on board, into the equipment, into the box, we have a computer and a software, and then we can display real-time some features. So you can display seismic, such as here. In the meantime, you can picture some frequency domain data and then cross sections, or you can here track some vehicle or event. And this can be done with our intuitive interface, which has been chosen by a lot of academics, because you can tune your data processing on board into the system, which has embedded high computation capabilities. So one way to expand all this is such as in telecommunication network, we can use repeater. So this has been demonstrated onshore so far. So after 50 kilometer, you can place a on-purpose repeater, and then you can put another 50 kilometer, and then you can simulate the fiber, and you will sense acoustics such as you were at 50 kilometer range. So this is a way to expand the range of the DAS. But if you have something to keep in mind after my talk is distance range is approximately less than 100 kilometer, no more. So what is it for? The simplest example to present for me is the seismic monitoring onshore. So here we have connected the DAS system, Phoebus A1R, to an existing telecommunication network onshore. It was in the Alps, and it was in a very, very silent area in the Alps, except at one point, an hydraulic power plant. And you can see on the DAS data, this plant here is a continuous noise. So this is a typical DAS data. So as a y-axis, you have the distance, and at the x-axis, you have the time. So you can see in gray, here in grayscale, the strain. So what you see here is an earthquake. So you can see the first arrival of the earthquake and then the secondary wave of the earthquake, such as you have one seismometer every 10 meters. It means like here you have 6 kilometers, it's just like you have 600 seismometer in one device at one end of your optical fiber network. And you can compare, it's not very clear on my slide here, but you can compare with stations, local stations, and you will have the same results at the same time. So it can be a tool for earthquake early warning, for example. This is an example onshore, but you can have the same offshore. So this is a couple of examples we have done with universities. So this is this first presented is with Stanford universities. They wanted to measure ocean noise, and it was in Monterey Bay with an optical subsea optical fiber cable. It was 52 kilometer long, and it was deployed in shallow water from 0 to 30 kilometer, and then entering deeper water, let's say. And here you can see in the frequency domain at 10-1 hertz, so microseismic domain, you can see this ocean wave spectrum, and it's decreasing here because we are entering deeper water. But you can see the noise is not increasing, meaning that you can be accurate even at 50 kilometers. Another one, even more, much more, let's say, pushy or much more complete, was published in Nature Communication by Anthony Sladen and this group of research. And Phoebus Optics was part of this work, actively part of this work. So we have connected the DAS to a 40 kilometer underwater cable, which was connected from the land to subsea experiment. And they have measured the same way ocean noise, ocean solid earth interactions. So you can see it's the same graph as you've seen before, but we can see even more. What I want to point here is the DAS signal is very rich. Indeed, here you can see plenty of things in that graph. So this is distance in the y-axis and time in x-axis. And you can see here, the first thing you see is stripes. I will come back to this afterwards, but here, first, the purpose of this experiment was to detect earthquake because it's a very seismic area. So we have detected earthquake. Here, hidden in that graph, in that rich signal, there is an earthquake. And if you compare the optical fiber record with the local seismic station, you have a match. So that's first thing. Second, you have some kind of oscillation. We already remarked at first sight, we have seen those oscillations. And those oscillations are due, and it has been verified, is due to suspensions of the cable. It means that it's very easy with DAS to detect suspensions. And plenty other types of data. Here you have waves, pure waves. So you have this diagonal pattern because the waves are propagating to the shore. You can see here on the first kilometer in shallow water, you can see the engines from boats. And then you can see some kind of unidentified waves, which may be due to the cable itself vibrating within the effect of the flow, or here the start of the earthquake. So this said, we are now starting a collaboration with EllaLink, and we're going to perform in a few days. It's maybe on the 21st of January, GeoLab experiment. So it has been presented, highly presented before, but the cable will start here in Funchal, and then we're going to scan all this zone here close to Madeira, those 50 kilometers. And so what we can do is that, first, we can do earthquake detection, as I demonstrated. We can see ocean response, ocean noise, suspension zone detection, which can be interesting for the cable deployment. And one of the purpose will be to see the behavior of the measurement the first days just after deployment. And we can do animal detection, vehicle detection, everything creating a vibration underwater. And finally, I wanted to say a white paper will be published at the end of the experiment, sharing the knowledge, and hopefully it will be a reference case study. Thank you very much.
Thank you, Vincent. I appreciate it. Some of the insights that Vincent talked about are vital to to develop from an infrastructure standpoint. But the things that many of us have heard over the past 10 or 15 years is that there could be some nefarious activities that can occur as a result of gaining this kind of DAS information and other types of information. So part of our challenge as a community is really to try and emphasize to governments that this is research information, and tsunami early warning, earthquake detection, all of those things are vitally important for saving lives, as we've learned from places like Indonesia. If there had been an earlier warning system, many more lives may have been saved. Same in Japan. So this research activity is vitally important. And the more that we can allow the research community to utilize it, I think the more and more things we're going to find. As a part of that, there is a legal regime that needs to be hurdled. And I'll ask Kent Bressie to come in and talk to some of that, because he's been involved with the JTF for over 10 years and understands some of the sensitivities there. So Kent, I'll turn it over to you.
Great, thanks, Tony. And thanks to the other presenters for providing a really great overview of both commercial developments and technological developments in this area. For those of you who don't know me, I am a partner with the law firm of Harris, Wiltshire & Grannis in Washington, D.C. I also serve as the legal advisor to the International Cable Protection Committee. And as Tony noted, I've been involved with the JTF for some time. I had previously served as the legal advisor to the Joint Task Force, although I no longer serve in that capacity. So I'd like to talk briefly about the legal environment and governmental concerns for different kinds of marine data gathering. This is an exciting area for innovation, but it's also one that poses some particular challenges from a legal and regulatory perspective. In particular, the Law of the Sea Convention, the United Nations Law of the Sea Convention, or UNCLOS, which we often simply refer to as the Law of the Sea. It's been accepted, ratified by most of the world's states, or even recognized by those who have not even signed. Treats telecommunications activities, energy, and marine scientific research as different and discrete activities. Coastal states also take differing interpretations of the law of the sea. And so this means that there's quite a bit of variation from country to country. Some countries are not sensitive about marine data gathering activities. Others are sensitive purely for jurisdictional reasons. Some others more for security reasons. And so I think it's important for the industry to understand these complexities to allow the technology to develop further and be applied, and also to understand how this sort of marine data gathering can actually be a cable protection tool. And I think that's the message that governments are probably missing the most. So the JTF was focused originally principally just on smart cables, with the potential addition of sensors in repeaters or as external peripherals. But now with distributed acoustic sensing, or DAS, we have a lot of new potential applications with marine data gathering, and also with data analytics, as best exemplified by a recent post on Google's main blog. It's possible to use existing data on a secondary basis from existing submarine cable systems, as Google has done with Curry, and working with scientists at Caltech to analyze that data for earthquake detection purposes. That information already exists. It simply is not always being used with a lot of these systems. So ideally, governments will recognize that marine data gathering can improve infrastructure protection and data gathering about the marine environment and disaster warning. But there is certainly the risk in particular regions or with particular countries that this could become a pretext for trying to regulate cables further offshore, the jurisdictional creep problem that we worry about, which can increase costs and delays for installation and repair. It could lead certain governments to mandate particular technologies, which some cable operators have long been concerned about as potentially compromising performance. And some governments are still going to view marine data gathering as a security threat or a reason for making cables targets. So when we hear discussion about being able to detect any kind of vibration in the water, that is sort of the worst nightmare of the world's navies who are trying to protect submarines from detection. So just briefly, the Law of the Sea Convention, and this is an image, I wrote a report for the Joint Task Force almost 8 years ago now, looking at some of the key legal and regulatory issues. Those remain mostly unchanged, although the technologies have evolved significantly and the security sensitivities have increased. But in general, coastal states have the right to regulate and grant authorizations for the conduct of marine scientific research in their EEZs, which extend 200 nautical miles offshore, and on their continental shelves, which extend at least 200 nautical miles offshore. Within the territorial sea, that's 12 nautical miles. I should actually toggle to the graphic here so that you can see this. So I was just speaking of the exclusive economic zone here in the center and the continental shelf. Closer to shore, the territorial sea, the coastal state can treat that as its territory It also has the right to regulate and authorize marine scientific research in that area. There are elaborate provisions in the Law of the Sea Convention about the conduct of marine scientific research. But most critically, the treaty doesn't actually provide a definition of what marine scientific research is. And this allows coastal states to assert it's whatever they think it means. And we have seen coastal states certainly do that. And so this is one of the potential difficulties in with some states. There's not always regulatory clarity or limitations on how they can apply this concept. So this set of rights and responsibilities for marine scientific research can clash with those for submarine cables under the Law of the Sea Convention. Although not all states observe all of these limitations on jurisdiction, again, going back to the jurisdictional chart, within the EEZ and on the continental shelf, coastal states are not supposed to assert permitting requirements for submarine cable installation and repair, although some certainly do. And so the concern here is that governments could have a pretext for asserting that cables that have marine data gathering capabilities should be subject to additional regulation farther from the shore. As with the lack of a definition of marine scientific research, the Law of the Sea Convention also doesn't define the term submarine cable, although I think we have a pretty good understanding in this industry of what that means. The lack of a definition there can also create some issues. So just a bit more about the Law of the Sea Convention's provisions for marine scientific research. These grant coastal states the right to do these particular things, but in many cases, coastal states don't apply all of these restrictions or consent requirements because they don't view marine scientific research as particularly problematic. Some states also have very permissive processes for allowing foreign researchers to come and conduct scientific activities within their EEZ or continental shelf areas. But there is a consent requirement. The understanding is that it will normally be granted if conducted for peaceful purposes and to increase scientific knowledge. It can be withheld if it's used as a pretext for things like identifying salt domes for oil and gas resources, for example, or identifying other resources of the EEZ or the continental shelf. If it involves more invasive or destructive activities like the use of explosives, drilling, or introduction of harmful substances in the marine environment, or involves the construction of artificial islands, installations, or structures. All of this can mean that if a submarine cable has capabilities that are viewed as marine scientific research, it can threaten delay. The Law of the Sea Convention provides that consent should be sought at least 6 months in advance. It also provides that the consent be sought by another state, not by a company. And so governments make requests of other governments for marine scientific research activities. If it's a domestic activity, in general, most states do not require their own companies or individuals to obtain a permission for anything that seems like marine scientific research. There's nothing that prohibits coastal states from imposing fees for the conduct of marine scientific research. The Law of the Sea Convention requires that the coastal state in whose EEZ or on whose continental shelf the activity is conducted, it grants them the right to participate, and that includes having persons on vessels and involved in other project development activities. And it also imposes an obligation to share data with the coastal state. And some states, of course, require the public dissemination of data. So if part of the business plan of a submarine cable operator with marine data is to commercialize that data. That might conflict with the obligation to share it with the coastal state for free. So just briefly about the two principal concerns that the industry needs to manage here. The first with jurisdictional creep. Coastal states are always looking for pretexts to try to regulate further offshore. This really undermines one of the basic premises of the Law of the Sea Convention, which states in its preamble the desirability of promoting international communications. And that's why there are some fairly unique rights and freedoms granted to submarine cable operators in that treaty. Coastal states are constantly undermining that by seeking to go farther offshore, either to prove their territorial claims, to assert their security interests, a host of policy considerations. And they use a variety of legal arguments, arguing that cables are installations or structures when those are discrete categories under the treaty from submarine cables. But they also can potentially use marine data gathering to assert that it's marine scientific research. And particularly with sensing capabilities, if the sensing, depending on the capabilities of the technology, an external sensor and a repeater with DAS, if it can detect a wide range of vessels and activities, it potentially can raise security concerns for the coastal state. All of that ultimately goes to additional regulatory oversight and potential costs and time delays. With security, the second particular problem that I think the industry needs to address, this has changed quite a bit since I wrote that report back in 2012. We're seeing so much more government scrutiny of the whole range of issues relating to submarine cables. And there's a lot of concern also about protecting submarine cables from intentional damage and sabotage. When we're talking about sensing capabilities, governments may have conflicting objectives as a consequence, because of course sensing can help identify potential threats to cables, particularly with DAS and nearshore areas. The principal threats to cables are fishing and anchoring. And if there's a way to actually identify proximate vessels that might damage a cable and actually contact them directly by radio or through a Coast Guard, that can help to protect cables, certainly with the front haul system as well. These technologies have long been deployed effectively in terrestrial contexts. But governments remain suspicious, in part because industry's been, I think, hesitant to talk with a lot of governments about these technologies, and they are viewed with some suspicion, particularly with submarine detection. So ultimately, I think that governments can be educated about this to promote the good potential outcomes about cable protection, better data about the marine environment, disaster warning. But I think we also need to be realistic, particularly with some governments that take more unreasonable views of their jurisdiction, inconsistent with international law, or that are particularly sensitive to security matters, that this can lead to jurisdictional creep and can trigger additional regulatory burdens, or could just be outright prohibitions because the technology is viewed as a threat. So with that, I will turn it back to Tony.
Okay, thank you, Kent. Those legal insights are critically important for understanding the industry's challenge. And that goes to regulators, that goes to cable developers, certainly suppliers as well. So all of those things put together, what have we sort of touched on today that's important? I want to bring all the panelists in, and we're going to talk through some of these issues for a few minutes and also take questions from the audience. So I'll leave it a minute for everybody to turn their cameras on and unmute for the team. And thank you all so much for your presentation so far. Let's talk a little bit about some of the things that are most important. And one of the things I wanted to get to from a Genesis standpoint, and this will go to you both, Chris and Gavin, is what are the things that really sort of made this possible to happen? And what are the insights that you think are important to take forward for other cable operators and developers? I know Philippe gave you some insights, Gavin, and so if you want to talk to those a little bit, and then we'll get down into some of the other subject matter. But go ahead, please.
I can take it first and then pass it over to Chris. I think the insight from the EllaLink perspective, Tony, is that from the outset, we had a motivated group of organizations who really wanted this to happen. So we had a cross-section of skills from the infrastructure side being EMACOM and EllaLink, the research networks being GEANT and the NRENs, and also having FCT and ANACOM. So having that governmental support was crucial. So without that whole picture put together, this wouldn't have happened.
Go ahead, Chris. Did you want to?
Sure. Sorry, I was just trying to unmute then and looking silly. Yeah, so I think in terms of what instigated the GeoLab, that's obviously the cable construction between Brazil and Portugal, and what came before that was about I think it was in 2002. The research and education networks in Latin America were working very closely with the research and education networks in Europe. And between the two, a dialogue was established. The European Commission got involved, and there are obviously lots of crossovers in terms of the research that's performed both in Europe and in Latin America. Astronomy is a key example, due to all of the astronomical telescopes that are based in Latin America. And Europe needs to get access to that data. And the same for Latin American researchers. They need access to the data that's in Europe. And through that, that's where the Bella Consortium started. So it's 11 research and education networks, both in Latin America and in Europe, working together. GEANT being the European operator, Red Clara being the Latin American operator, or Latin American research or regional research and education network. And without that project, I think that was one of the key anchor tenants of the EllaLink project. And it's through that we've been able to get the funding to build this direct cable between the two continents. And from that, that's where the groundwork, the foundation has basically been established for something like this to come to fruition, or the GeoLab to come to fruition. So without the clear need and benefit and the involvement of the research and education community in the main subsea cable, I think we would have struggled to have something like GeoLab happen right now. And it's taken a number of years for that to occur. But slowly but surely, I'm hoping that this, and I said it in the question and answer section, I'm hoping that the GeoLab will act as a proof of concept for future infrastructures like GeoLab, so that we can replicate this elsewhere in the world.
Great, thanks, Chris. Ken, you've been around for 10 years working on a lot of this, and you work for JTF as well. I mean, what do you think took so long? How come more projects like this, especially in places like the Ring of Fire, where these kinds of projects would be much more helpful, haven't come to pass earlier?
Well, I think it's a number of factors. The principal one is somebody has to pay for it. And I think that with configurations that would put sensors in repeater housings or potentially as external peripherals, there were a lot more performance related concerns as well from owners about how that would affect their activities, and also, how the data, which doesn't consume a lot of bandwidth, but on whose fiber pair would that travel between the sensors and the endpoints for the cable. So I've always articulated a view that I think this is an area that's ripe for experimentation. And I think particularly with DAS technologies, and particularly with what we're seeing with EllaLink, with governments who are not particularly concerned about this and not trying to impose a lot of regulatory burdens, it does provide a good test case to see how this can develop. There is support for it as part of the business case for this project. And so I think that that is important. With some of the sensing technologies, I think there are always going to be limits in terms of the data with scientific utility if it's just piggybacking on a commercial telecommunications system. And with disaster warning in some parts of the world, the technologies aren't going to provide enough warning to actually save lives. And so I think that limits the interest in some scenarios where the earthquakes are very close to shore. Indonesia is a good example of that.
Yep, I understand. And I think we were on a committee once, and they talked about having a couple of minutes. That might be helpful for many. So it doesn't, the commitment is one component. The time is the other piece that for people to react. So, if you could talk to that for just a second, Kent, and then I'll turn it over to Vincent, just to, when we talk about early warning capability, especially for earthquakes and tsunamis, I don't want to use the entire length of the cable, but I would like to understand from a DAS perspective in that 50 to 200 kilometer range, how that would be helpful from an early warning standpoint. And if a minute, 2 minutes is optimal for anyone to be able to get some warnings out to people. Go ahead, Ken, and then over to you, Vince.
Sure. So for the benefit of our audience, Tony's referencing an initiative within the United Nations Economic and Social Committee for the Asia Pacific, UNSCAP, which is based in Bangkok. And UNSCAP has held a series of originally in-person and now online workshops looking at disaster warning technologies in the Asia Pacific region, particularly for tsunami detection and warning. And they've been looking at different technologies, placing sensors on offshore oil and gas platforms, placing sensors on vessels, and using submarine cables for marine data gathering for those purposes. This is a critical issue for both for UNSCAP and for governments in the region. But I think that it was particularly interesting to hear from representatives of the Indonesian government talking about what is and is not possible in terms of early warning systems, given the particular seafloor geology and plate locations in Indonesia. That may be a region where some kind of early warning system has more limited utility than it might where underwater earthquakes occur further from shore. And so I think there's continuing interest, but I think also a sense of realism with governments in the region. Of course, we also, Japan has quite a bit of experience in building dedicated earthquake sensing systems, tsunami detection systems that are purely for those purposes, ringing Japan, which obviously has had significant issues with those risks. I think in many cases, those earthquakes have occurred further offshore, which has allowed for additional warning time.
So, Vincent, if you could talk about sort of the importance of DAS in that 50 to 250, and maybe pushing it out a little further as the technology develops. I mean, what are the things that you hope to grasp or to be able to utilize to get that information into, it's milliseconds, of course, to get that information into shore stations to be able to warn citizens?
Yes, first of all, what one has to understand is that the DAS is not magic. You're just sensing the vibration where the cable is, and then the information goes very fast to the shore, but you're still something like 100 kilometers close to the shore. So if you have a subsea seismic station with an optical fiber, telecommunication optical fiber, one can say it's the same, but not. It's not the same, because here you have a distributed sensing, meaning you have this shape of wave I showed you before. So with this shape, the scientists, they can model it. The experts, they can model the distribution of waves, and then can find the hypocenter, the epicenter, and many parameters from the earthquake or from tsunamis. That's why it is useful, but much more than, it's not earlier than other ways of measuring earthquakes. It's not very faster, actually. It's, let's say, much more exhaustive view of what happens.
Right. So I'm guessing that, Chris, from your perspective, there's an awful, as I think both you and Vincent mentioned, there's an awful lot of information that's collected on a daily basis. So the critical piece of that is really sort of modeling data when you see certain kinds of activities that happen. I mean, in this day and age, we have dart buoys and we have satellites and other things that help with that. But there really is sort of a time dimension to it that says we're going to need to collect an awful lot of information so that we can have these models that say, when X happens, Y will occur.
Yeah, and I think it's important to mention as well that that this technology is largely unproven from like a wider perspective when it comes to tsunami warning and earthquake detection. It can detect it, and it looks very promising. But this is what the geolab's there to try and provide. It's a facility that will be able to test out these types of technologies on, to try out the processes and the procedures that civil protection authorities will need to try and implement in order to realize a tsunami warning system or an earthquake detection system using DAS or whatever technology seems to work best. But at the moment, DAS seems like the most promising technology at the moment for this type of setup. And yeah, I think that there's two parts to it as well. There's the part of civil protection and responding really quickly to the information that's made available, but then there's the longer term research where people can dig into the data to extract meaningful information that will push the boundaries of science, and that's hopefully what this type of infrastructure will provide, is that ability to have both the near real time extraction of the data for societal benefit, but also for the long term research community's requirements.
Right. Thank you. One of the things that we touched on topically beyond early warning and tsunamis is really aggression. And ICPC and others deal with the aggression zone that in general is near shore. These types of DAS sensors, Gavin, from your perspective, I mean, EllaLink is probably one of the first to adopt it. So when we talk about things like suspensions and anchoring, there are some things that you can do from a geofencing standpoint and cable protection zone standpoint that will be helpful for you as an operator. So do you see those things as useful down the line and as potential as potentially good pieces to add to your network?
Absolutely. As I was saying earlier on, Tony, you know, aside from the attraction of providing this infrastructure to the likes of GEANT and Fabus to give something back to the community, those benefits to the commercial aspects of the cable are a crucial attraction for EllaLink. To have that additional layer of protection, to be able to detect suspension, and as you say, external aggression like fishing or anchorage, is there kind of at the moment a little bit with AIS, but we believe that the DAS will give us excellent additional protection, which just doesn't exist at the moment.
Kent, did you want to speak to that as well?
No, I think that this is an important area of technological development. And again, this is a technology that has already been deployed very successfully in terrestrial network concepts or contexts. And so I think that it's helpful as a discussion point for engaging with governments as well, because it conveys that these kinds of sensing technologies and data gathering are not just potential threats, but they're also a potential security solution.
Great, thanks. And this sort of points to tools in the toolkit for research scientists to be able to utilize in order to identify patterns going forward, much like that you mentioned Google's SOP look at things when they were working with the folks out in California. I mean, that's an interesting development in much deeper water, but are those things that are those tools that will be useful going forward, Vincent? Do you think SOP? If you could talk to them.
It's kind of complementary technology. Yeah, it's not the same as DAS. DAS your exhaustive view, but local. With SOP, you have full view, but global, meaning you have one line is one data, another line. So if you have plenty of lines, such as Google, you have plenty of information, but it's not the same way. DAS, it's localized, so it's much more, I would say, useful for local model, and SOP should be useful for much more global thing. And I see questions in the Q&As, and they ask for example, if you have a 5,000 kilometer long cable, you may want to use DAS at both ends of the cable and SOP on the global cable. And if there are branches, you want to use SOP on all the branches.
And you said in the chat there was a question that
how could a 4.7 thousand kilometer cable utilize DAS successfully? And actually, it's a good question, because the only thing we can do is use it at one end or the other, if both are accessible, or maybe some branches in the middle, some islands, or I don't know. And to adapt, we will need a dark fiber, meaning dark where there is no signal. So this can be another topic.
Right. That goes back to what you said earlier, Kent, and that's about paying for these things. You know, telecom cables are, you know, hundreds of millions of dollars. We're lucky in this case, or not lucky, but we're just fortunate in this case with GEANT and ANACOM and others, that there was a need at the time, and they put forward a public-private partnership. Do you see that as a model going forward that is sustainable with other government actors as well?
I think it just depends on the particular cable owners, the jurisdictions. The perennial problem here has been that scientists want data, but don't have the money to pay for it. And cable owners are concerned that imposition of regulatory mandates is going to make it more expensive for them to operate their cables and could compromise the performance characteristics of those cables. So the more innovation and experimentation there is, the more parties I think are going to get comfortable in particular areas with working through some of the performance related concerns or figuring out on whose fiber pair is the data going to be transmitted, if there's going to be some arrangement like that. But it's just going to vary in part by state. I mean, certain countries are very, very sensitive. Some are increasingly sensitive in a way that they haven't been in the past. The United States has historically been very permissive with marine scientific research. I think it's taking a harder look at requests from other governments to conduct MSR in the US EEZ. But it's not just the United States. I mean, historically, Peru and Argentina have probably been the most sensitive about their EEZ and continental shelf areas, and certainly China. And if you layer on the issue of territorial claims and disputed marine areas, that can make application, the addition of these activities even more complicated.
Yeah, it would seem so. Back to sort of one of the tenets that we're talking to today is that marine data sovereignty. And Chris, you mentioned that the data points and all the information that's collected is going to be transmitted to the science community through Portugal and through others. Now, I'll ask you first, and then Kent, if you could just comment on the sovereignty issues. That piece I think we all sort of need to understand, because those are the data points that are most concerning to governments. So Chris, if you could please.
Sure. And this kind of goes in a way to one of the questions that I answered from Peter Fisk in the Q&A part. But the one thing to make everyone aware of as well is that the data that's generated, the Portuguese government have said we'd like to be acknowledged as the source of the data. And in terms of the distribution of that data to the wider global community, as long as the Portuguese government can be acknowledged and credited with the source of the data, they're happy to allow us to perform this type of research on the cable. We are working quite closely with ANACOM, the government regulator, and also with FCT, the National Research and Education Network, who are a part of the Portuguese government as well. So with this collaboration between all of the partners involved in GeoLab, we're hoping that the governance structure that we've got in place will allow us to be able to disseminate information more widely, while at the same time kind of easing the regulatory burden for researchers, but also going some way to try and appease any concerns that there might be in distributing this data more widely.
It's important for governments to understand and recognize different kinds of data here, because I think certain kinds of data should not be treated as marine scientific research, subject to formal or informal consent requirements, data sharing, review. If it relates to the performance of the cable, it should be governed by the legal regime that governs submarine cables in the EEZ and on the continental shelf. If it is marine data gathering for scientific purposes, that's where I think it's appropriate. And I think this is the approach that's reflected with EllaLink here, where it's not simply related to the commercial telecommunications mission of the cable, that is subject to some of the requirements and engagement with the government asserting jurisdiction in the EEZ and in the territorial sea. But I think we need to be wary of living in a world where governments are going to start asserting that they get access to all data for whether it's for sensing purposes or, of course, the communication stream itself. This remains a highly sensitive subject with government surveillance. And interesting that one of the original expressions of interest about a cable on the route served by EllaLink was a concern by the Brazilian government that the United States was hoovering up data on all cables landing in the United States. And it wanted to send data on a facility that was not going through the United States. So I think continuing to define what is relating to telecommunications versus science is important here.
Right. So maybe it's important that we sort of have a body of standards that we expect to derive information and be able to utilize only that grouping or standard of information to facilitate cross-country transfers or research community transfers. And maybe that will have a settling effect on some governments or not.
Well, I think for scientific data, again, some governments are, we see this with the Bella Consortium. We have a number of institutions in different countries that are collaborating on this, and it isn't raising particular sensitivities. Again, I think so much depends on where this activity is occurring and which governments are potentially implicated. I don't think that we want to be trying to impose, we're not going to reach agreement. Governments have been fighting about what the term marine scientific research means for 50 years.
Sure.
That's not going to be resolved. It's a bigger fight than we have here. I think the important thing is for allow innovation to take place and for what I call the greening of cables in certain respects with some of these more social aspects to be developed without provoking the parade of horribles that some have long worried about with jurisdictional creep and viewing cables as targets.
Thank you. We have a few minutes left. And Jen and Layla, if you could go through the Q&A questions, I'd like to get some audience participation if we have some questions. And I think there are a few.
Sure. This question is for Kent. Kent, can you comment on the fact that all early adopters of SMART will involve governments, and so far they do not appear to see problems with legal, permitting, and security?
So I'm not sure which particular projects or test bed arrangements we're talking about here, or what the particular sensing technology is. So I guess it's hard for me to comment on specifics here. There's been a lot of discussion within the JTF about testbed activities and trying to apply particular technologies. If the experimentation with sensing and marine data gathering is occurring within the jurisdictional areas of a single state, and certainly that's what we have with EllaLink, at least as between Madeira and Portugal, it's one sovereign, then I've long believed that that was the area where it was going to be easiest to innovate because there was no foreign element that was potentially creating security concerns or provoking jurisdictional fears on the part of the government. And I think we also see some of that potentially on a regional basis. It's with the long haul transoceanic systems that are going through the jurisdictional areas of multiple states that I think is probably going to be the most challenging, at least at the outset, which is why when I was the legal advisor for the JTF, I kept urging experiment locally or regionally to see what might be possible before trying to take on some of these bigger, more political issues.
Thank you, Jen, or I'm sorry, Layla. I think we have time for maybe one more question and then we'll do a wrap.
Okay, would EllaLink GeoLab consider adding State of Polarization between Funchal and Sines, both landing being Portugal? What would it take?
So I guess I should be the one to answer that one. As at the moment, we've got a number of optical channels that we've got available to use for research. But I think the best answer I could give is talk to me. And if we can't do it on the EllaLink cable, then the GEANT backbone could be an alternative place where we could try and test this type of research out. It's something that we'd like to try and support if we can.
Okay, I think we have time for one more question. Last question. NSF is interested in exploring the introduction of a subsea telecom cable between NZ and its largest Antarctic research station, McMurdo. And it is also interested in the concept of including marine science research capability. What are the key points that NSF should consider, noting that from 60 seconds and higher latitudes, the marine environment is governed under the Antarctic Treaty. US and NZ are signatories. Also, there is NREN interest by NSF in the cable. How can the NREN community support this initiative?
So I'll answer the first part of it because it's a treaty question. The interplay between the Antarctic Treaty System and the Law of the Sea Convention is complicated. There are countries that have made territorial claims in Antarctica, and the Antarctic Treaty does not take a position on those claims, but it also prohibits signatory states from engaging in activities in Antarctica to advance those territorial claims. As noted in the question as well, the treaty governs the region, not just the continent of Antarctica, but south of 60 degrees latitude. And so that includes ocean areas as well. There are restrictions on activities that could be seen to have adverse environmental impacts. I would direct everyone to ICPC's website and the compilation of peer-reviewed scientific research showing that cables are benign in the marine environment. But the Antarctic Treaty System is very much designed to foster scientific research in Antarctica, and a cable that would serve those interests would certainly be consistent with the purposes of the treaty. Of course, with the Law of the Sea Convention, the Law of the Sea Convention doesn't take positions on disputed territory, but it does allow states to impose particular restrictions in their territorial areas. And if it's marine scientific research within the EEZ. So I think there's certainly the possibility, although I think it's unlikely, that a claimant state for territory in Antarctica could assert that it has the right to restrict particular activities. I think that would violate the Antarctic Treaty prohibitions on advancing territorial claims. I'd be happy to talk further about those issues offline, because it could be the subject of a separate conference.
I'd definitely like to be involved in that. I mean, I can't talk from, well, I can't represent GEANT or the EC on that type of question or responding to that type of question. But personally speaking, I think that there's a strong case for being involved in a submarine cable between New Zealand and Antarctica, especially considering the amount of research stations near McMurdo, not just the US base, but also Zucchelli Station, which is an Italian research base. So yeah, I think I'd definitely be open to discussing that with others who might be interested in trying to achieve that.
Great, thank you. How are we doing for time? Layla, we have just a few minutes left.
Yeah, just a few seconds actually.
Okay. Well, well, thank you all to all the presenters. It's been a great session, and I've learned a lot, and I hope it's been helpful for the community as well. All of this research information is really going toward the greater good, and there's an awful lot that we need to do as a community to make sure that we inform governments and government partners and cable developers and suppliers that there's some terrific research out there. And conferences like these and others will help to facilitate more conversation and certainly more outcomes like EllaLink and others. So with that, thank you all so much. Again, to our sponsor, Suboptic. There are some terrific posters as well that are out there on the website. Please take a look at some of those. And there will be a great bibliography that's available out there as well on some of these topics, both in ITU and some of the work that Dr. Howe has done with JTF. So thank you again to all of the presenters, and thank you, Layla and Jen, for your help as well.
Following the telegeography session, take a visit to the submarine cable poster sessions in the Sub Cable Networking Lounge. Want to catch up on each day's happenings? Visit the PTC TV exhibit booth in the PTC Hub. Is it time for a break? Need a little pick-me-up? If so, stop into Infinera's Networking Lounge for a free cup of coffee.